So, as I represent my research group on singular optics, as you expected, it will be optical vortices too in my report. So, as no, okay. So, as you know, when the optical beam passes through a crystal, for example, when the initial polarization state will be linear or tilted on some degrees, for example, as 45 degrees, in the crystal section it will be changed periodically again. So then we scan, we can find the different states of polarization from linear to circular and back. Another thing, then the light path is uniaxial crystal at the birefringence. So we can get the ordinary red one and extraordinary beam. The main difference between them is orthogonal polarization states. If we put the initial polarization on the 45 degrees or the circular polarization in the input of the crystal. So we discuss now the case then the optical axis is strictly perpendicular to the beam axis. Our theoretical model is our theoretical model is built on the simple form. The first one is the Gaussian beam. It's a solution of Helmholtz's equation. Only Gaussian beam. It has two parameters, x and y, its coordinates, and beam based. So it's nothing strange. But the second part and the interference pattern of these two beams, ordinary and extraordinary one, is merely elliptically deformed. So we can get this conoscopic pattern in the circular polarization state, some of one left, right, or left. So when we construct the beam, this embedded optical vortex, the next part of this equation is optical vortex here. So we can see the typical minimum intensity on its center and the undetermined phase. This undetermination will be realized like a spiral phase map. So this is quite interesting because optical vortices is very sensitive to any varying of parameters in media, in optical fibers, etc. So we need to find a way how to control these parameters without disturbance of the whole field. So we decided to use uniaxial crystal for these purposes. Why? Because when we rotate, for example, our crystal, it may, due to the birefringence and difference between ordinary and extraordinary beam, it can transform our initial beam to the singular one at first and permit to control some position of optical vortices embedded to the beam. For example, in this case, we put to the input beam a vortex with small shift from the optical center or from the beam center. And then we rotate the crystal. The output field can be imagined as a circle trajectory of vortex during the rotation. This radius of this trajectory can be expressed as It depends only from beam-based and crystal parameters. The next one is discovering of circular polarization components, the most interesting one, because in these components are two ordinary beams can be realized in interference pattern. So if we take a shifted vortex, so in ordinary beam it stay at the same side like in an initial beam, but in extraordinary beam, due to the elliptical deformation, it shifts merely, so we can receive two vortices. You remember we see the one spiral, but here we can see the first one, the second one, and the third. So we call this situation as topological dipole. It can annihilate because they have the opposite signs. You ask what about the sign of topological charge. So this state when we have a screw dislocation, we call it helicity wavefront. If the helicity is have a charge 1, the screw dislocation is only the spiral. When two spirals embedded one each in another. During the rotation of the crystal, we can observe the dynamics of singularities. It makes some interesting results because the vortices can be generated by crystals. They have the initial vortex, the vortex is generated, so they can interact between each other. And such wise we can build this trajectory of our interaction between vortices. The white circles marked here, it's burst points of optical vortices. They come through our field and can interact this initial vortex in the center of our beam. So if you mention this picture, these lines, these conoscopic patterns have typical lines. So the symmetry repeats also here. We have the lines along which the vortices can travel to the beam center. And so they also experimentally prove our investigations. We built this experimental setup where they use only helium-neon laser and crystal of quartz. Only small quartz with 1 centimeter cube, and allows us to control beam parameters. For example, it generates the vortex this sign +1. For example, the spiral will be have the right direction, and the sign -1. We also have the helicity in this side and backwards, left and right. So this is the same case. Here you can see the typical interference if we put the flat wavefront to this point. And you see the typical quarks. You ask, what about the hologram, which we use for generation of optical vortex? Holograms is this part of picture, for example, if we crop this, and when we enlight it by Gaussian beam, it becomes singular, this dark spot in the center. So like a tornado, and you know tornado has a area this low pressure and it absorbing everything inside of it. So the vortex is the same structure with a minimum intensity on this axis. It can absorb microparticles around the beam. So it may be used for optical trapping, optical tweezers, and widely used already. So we proved that crystals can generate in low visible light, for example. We don't investigate the terahertz technology yet, but I hope it will be soon. So what are the possible applications of such investigation? First, the generation of optical vortices with different phase profiles. It depends from the orbital momentum, because when the orbital momentum is large, you can absorb more particles. The particles can be large and so on. The polarization controlling, we can build a very simple polarization or not. And the second one, the vortex generation, and the most interesting is the phase or vortex microscope. We can scan by this vortex because the phase very sensitive to some disalignment of surface. It can be surface analyzer with resolution of tens nanometers. And so on. So it's very perspective, and I hope you enjoyed this presentation. Thank you very much for your attention.
Thank you, very good talk.